actual formula of a compound. Not hard to do. And that is how they determine the formulas. They find the empirical formula this way. They know the mass of what they start with. They decompose the compound into the elements that break it up. And data, they can prove what the actual compound is. The last couple days, we've been working on adding up formula mass or the molar mass of compounds. In a sense, we're doing a similar problem, but in a way, we're working it backwards. We're working it backwards. We have posted 6 D15 notes determining the empirical formula of a compound from percent composition data. Remember that an empirical formula gives you the mole-to-mole ratios. It gives you the mole-to-mole ratios of the elements that are in that compound. And an empirical formula gives those ratios in the smallest ratios you have. They reduce them, if you can remember. When we added up the molar mass of a compound, we started with how many moles of each element were in the compound, yes? And we multiplied that by the mass from the periodic table. And then we added it up. So if we were going to find the molar mass of water, we would have done something like this. Finding the molar mass of water, we'd be like, how many grams of hydrogen are in water? We'd be like, well, there are 2 moles of hydrogen in water because the formula is H2O. There are 2 moles of hydrogen in water. And we know if this is on the top, we know that we want it on the bottom of our expression. And we look on the periodic table and we'd be like, water, hydrogen is 1.008 grams. So we would have 2 times 1.008. That's 2.016 grams of hydrogen. Then we'd be like, how many grams of oxygen are in water? Well, the formula is H2O, so there is 1 mole of O. If this is on the top, we want it on the bottom, so it cancels out. If we're looking for grams, remember, grams goes on the top. That would be 16.00 grams of oxygen. Then we would add that up. The molar mass of water, 1 mole of water is 18.0, and we would round that up to 2 grams. Each calculation, we should start off with a heading. We're determining the molar mass of water. There's our heading. Here is our work. Double check. Does everything have a label on there? Every number needs what the unit is and what it belongs to. Double check. Sometimes it's easy to leave them off. This is what we learned to do the other day. Except now we are going to be starting not with these numbers. We're not starting with these numbers. We're going to work backwards and find those ratios. We're going to find those ratios. We're trying to find how many moles there are based on a certain number of grams of each substance or a certain percent of that substance in the compound. Same kind of problem, working backwards. Same rules apply. Every number needs a unit and what it belongs to. You're like, we don't know what you're talking about working backwards. You'll see. We're starting with something different here. We're not starting with the moles. We're trying to find the mole-to-mole ratios. That's what we're trying to find. Here we go. I hope. You know what I need to do? This mouse never, and even other teachers walk in and they're like, your mouse never shows up on your board. You know see that little thing? Never shows up. Like when I try to use the mouse so that I can scroll on the screen, it never shows up. I've got a solution. I think I can fix it. You're like, think of all the teachers that you have. Which teacher is probably most technologically proficient? Of all the teachers you have, it's who? Mr. Townsend.
Yeah.
He's the IT person, but you're saying he knows more than I do?
Yes.
You're actually going to say that?
Yes.
To me?
Yes.
Well, let me show you right now with my solution between being able to find where that little thing is on my board, the mouse. I will prove that you'll be like me. I'm sure you're going to write an apology letter here in a second. I should put cheese out. If I hang cheese here, the mouse will go straight to the board, right? Yeah. There you go. You don't have to apologize. It's true. You're like, I'm with you now. Here we go. Finding the empirical formula. Here's an example problem. Believe it or not, I have coffee in here, and it is not decaf. You're like, that explains why you're hyper. It might. I don't know. There's caffeine in my coffee. It is a stimulant. If we break down the caffeine, if we extract the caffeine from the coffee and we break it down, we would find out that caffeine is 48.48. Maybe that's supposed to be 9. 48.49% carbon, 5.15% hydrogen, 28.87% nitrogen, and 16.49% oxygen. Where do they get those percents? They mass the caffeine that they're breaking down, yes? Then they mass each of those elements that come out of it. They divide the mass of each element divided by the mass of the whole. They get the percent. We already know how to do those. That's where those percents came from. But now they're wanting the empirical formula for caffeine. They want to know what the formula is. What is the formula? C what? H what? N what? O what? That's what they're trying to find. And a formula gives the mole-to-mole ratios reduced of each element in that compound when we're looking for the empirical formula. So how do we do this? How do we go from a percent? And we already know the law of definite or constant composition. You remember that law from way back? It all comes back. The beauty of chemistry is stuff we learned all the way back in September. Do you remember when we went over the law of conservation of matter and mass? We went over the law of definite or constant composition, and we went over the law of multiple proportions. Law of multiple proportions was Dalton. Conservation of mass was Lavoisier. Law of definite or constant composition, Proust's law or Proust law. All it says is a given compound is always made up of the same elements joining in the same ratios by mass. So if I have a 100-gram sample of caffeine, I have a 100-gram sample of caffeine. How many grams of it are carbon? If 48.48% of it is carbon, how many grams are carbon? 48.48. I think that's supposed to be a 9. We would have to add all those back up. How many grams of it are hydrogen? 5.15. How many grams of it are nitrogen? 28.87. How many grams of it are oxygen? 16.49. All you did was took a 100-gram sample. We learned to do this calculation. We just did this calculation on last night's homework and the night before. If you know how many grams your sample is, you just take the percent, put it back in decimal form, and multiply it by the grams of the sample. That's all you did. That's all you did there. I could have assumed that I had a 10-gram sample. Then it would have been 4.848, yes? Then it would have been 0.515. Then it would have been 2.887. Then it would have been 1.6. Proust's law says no matter what the sample size is, the percents are going to remain the same. So you can assume your sample size is anything you want. Conveniently, you assume it's 100 grams. So do I know how many grams of each would be in that sample? Yes. I can use that information to find the mole-to-mole ratios. This time, we're looking for moles. The problem that we already learned to do, we were looking for grams, and we were starting with moles, yes? We were looking for grams, and we started with moles. Here, we're looking for moles, and we're starting with grams. If I can convert moles to grams, I certainly can convert grams back to moles using the periodic table of elements. If I know that I have 48.49 grams of carbon in the sample, I can use the periodic table. 1 mole of carbon is 12.01 grams. That's my conversion factor. I can use the periodic table and say 1 mole of hydrogen is 1.008 grams. Grams are on top here, so I put them on the bottom. I'm looking for moles. It goes on top. What am I essentially multiplying by here in these conversion factors? You can always recognize conversion factors in chemistry. They put brackets around them. It looks like a railroad track. It looks like a railroad track. But when I am multiplying by the conversion factor, all I'm doing is changing the units. What am I really multiplying by in the conversion factor? We're just multiplying by 1. Cleverly written. You're like, I don't know what you're talking about, Mr. Hitmar. Well, look, do we know from the periodic table that 1 mole of carbon? I show you this. Do we know from the periodic table that 1 mole of carbon has a mass of 12.01 grams? Yes? Do you agree those two things are an equality? If we have an equality, can we divide one side by something, provided we divide the other side by the same thing? Yes. Yes, we can. I'm going to divide by 12.01 grams. Why? Well, if I divide this side by 12.01 grams, I can divide this side by 12.01 grams. If I do it to this side, I do it to this side. I have not destroyed the inequality, have I? What is 12.01 grams of carbon divided by 12.01 grams of carbon? That is 1. So 1 is equal to 1 mole of carbon over 12.01 grams of carbon. This 1 mole over 12 grams is really 1 in disguise. As I like to say, if you're a female, it would be this girls. This is 1 in disguise, or 1 in disguise if you're a male student. So I'm just going to take 1 written as 1 mole over 12.01 grams. That's what we're going to do. That's what we're going to hope to do. You're wondering why I have tape on my knuckle? Has anyone wondered that? What do you think I punched yesterday? Why would I have punched the smartboard yesterday? Someone's like, did you punch the smartboard yesterday? You've got tape on your hand. Are you just like losing it because your smartboard keeps freezing up and not letting you do anything? No, I actually didn't punch the smartboard. That would be stupid. I didn't punch the smartboard. I accidentally shut my hand in my hood of my truck. I'm like, ow. So we're going to, yes. We're going to replace. We're going to multiply each of those by 1, cleverly written, when this thing comes back on. And that will convert mass to moles. If we're starting with mass and we multiply by mole over mass, the mass cancels out. We're left with moles. Let's see how this should work. We hope. Here we go. There it is. Mole over mass, mole over mass, mole over mass. The periodic table will enable us to convert mass to moles. It will also enable us to convert moles to mass. So there's our moles. However, Do formulas give moles or do they give ratios of moles? Ratios of moles. They don't give actual moles, they give ratios of moles. So how do I get ratios out of 4.037, 511, 2016, and 1013? To get a ratio, we divide the smallest one into the rest. What is the smallest one of these? 1.031. So I divide all of these by 1.031. And that will give us ratios. 1.031. 1.031. You divide the smallest one into the rest to get ratios. That's what's happening right down here. We're dividing the smallest one. We get 3.916, 4.956, 1.999, and 1.000. Now, those numbers are not going to come out to exact whole numbers. Why won't this? 4.956 is very close to what? That is very close to 5. 3.916 is very close to what? 4. This 1.999999999999999 is very close to what? 2. Why are they not coming out to whole numbers? We were using data acquired from what? First of all, we used numbers from the periodic table. This number, this number, this number, this number are rounded. Secondly, when we do actual calculations, the numbers are rounded. When you put something on a balance, it's not going out to the gazillionth place. It's rounding. So none of the measurements are not going to be exact either. So don't let it surprise you if the numbers are not working out perfect. You want to know how old I am as a teacher? Do you see what I'm doing right now? Erasing the smart board because it's frozen up again. However, back in the old days of teaching, they didn't have smart boards. You're like, how old are you? I am so old that they used to use something called a chalkboard. You may have never seen a chalkboard. A chalkboard, you would write on stuff in chalk, or you would use overhead slides. When you used a chalkboard, you'd actually have to erase. You're like, how did you erase your board so well? Because I erased boards for years. Anyway, I didn't entertain any of you. Sorry. So, anyway, our 4 moles goes here. 5 we rounded goes there. Our 2 goes there. This is the empirical formula of caffeine. Very often when you do calculations, you have to look at those after you divide the ratios, after you try to find the ratios. Very often the numbers are not near a whole number. Did you see how the one we just did, they were all very close to a whole number? Very close meant like 3.9 is close to 4. Sometimes that's not going to happen. Here they're finding what is in a white powder. They analyzed the white powder. It was 43.64% phosphorus, 56.36% oxygen by mass, and they're asking for the empirical formula. What do? Assume we have a 100-gram sample. That would be 43.64 grams, 56.36 grams. And then we multiply those by a conversion factor. We're starting with grams. Grams are on the bottom. We're finding moles. It's on top. The grams of phosphorus and the grams of oxygen cancel out, leaving us with moles. Factor label method. But when we then go to get the mole-to-mole ratios, when we go to get the mole, this thing is really having a great moment here today. When we go to get the mole-to-mole ratios, what's the smallest moles there? 1.409. That's the smallest one. So we divide it into both, and this time we get 1 and 2.4. Is 2.4996 very close to 3? No. Is 2.4996 very close to 2? No. 2.4996 is very close to 2.5. When we find the mole ratios, we did not end up with whole numbers. When you don't end up with whole numbers, you have another step. You have to multiply all the moles that you now have by the smallest whole number. That would result in them being whole numbers. What's the smallest number I can multiply 2.5 by to make it a whole number? 2. If I multiply this one by 2 to make it a whole number, would I also have to multiply that one by 2 in order to maintain the ratios? What you do onto 1 mole, you do onto all. 2 times 2 is 2, or 1 times 2 is 2. 2.5 times 2 is 5. There's our empirical formula. What would I multiply something by if I did the mole-to-mole ratios and we had like 1.25 or maybe 1.24999496897493991? What would I multiply that by to make it a whole number? 1.2, essentially 5. You would multiply that by 4 is correct. Well done. What if I had like 3.33333333333? What would I multiply that by to make it a whole number? 3. What if we had 2.7489648325? That's very close to 2.75. What do you have to multiply something that's 0.75 by to make it a whole number? It would have to be 4, wouldn't it? 0.75 would be like in fraction, 3/4. You would multiply that by 4. 3/4 times 4, that would end up being 3. So we take that whole number by 4, it would make it a whole number. This is how we do. What if it ended up in a 0.67, some number with a 0.67? We would multiply that by what to make it a whole number? Some number with a 0.677777777777. What would you multiply that by? If you're saying 3, you understand what we're doing here. And if you're really confused, it's not hard to do. You could just take the number times 2. Did anything happen? Take the number times 3. Oh my gosh, it went to a whole number. Those are some of the ones that we would encounter. So if the number is actually closer to a fraction, you must multiply all of them by the smallest whole number. That gets us the empirical formula. Empirical formulas are extremely useful for salts. But what do we want if it is a substance that is not ionic, if it is a covalent substance, if it's 2 nonmetals together? The empirical formula is really not what we would want. The best formula to represent covalently bonded substances are what kind of formulas? Very good, students. Molecular formulas. If we know the empirical formula and we know the mass of the compound, we can find the molecular formula. It's telling you how to do this right here. In this example problem, we know the empirical formula is CH2O. The molecular formula, if the empirical formula is CH2O, that means it's been reduced. That doesn't mean it's a molecular formula. CH2O is covalent. It is a molecule. The actual molecular formula is going to be a multiple of that. It could be a multiple of 1, which means the real formula could be CH2O. Or it could be C2H4O2, or C3H6O3, or C4H8O4. A multiple of that. Because remember, the empirical formula is reduced. It can be reduced by 1, 2, 3, 4, 5, 6, 7, etc. So what we need to do is figure out what factor it was reduced by, and then multiply the empirical formula by that multiple to get the actual formula, the molecular formula. So if I know the real formula, or if I'm trying to find the actual molecular formula and I know the empirical formula, I can get this done. So in the problem above, we found out the empirical formula was what? P2O5, yes? That was the empirical formula. That doesn't mean that's a molecule. That doesn't mean that's the actual molecular formula. If we know that the real molecule has a mass of 283.88, I can find the real formula. Here's how I do it. I first find the formula of the molar mass, or in this case, the formula mass of the empirical formula. There were 2 phosphoruses. We multiply that by 30.97 AMUs over 1 atom. Where did I get that? Periodic table. I'm just finding the mass. There's 5 atoms of oxygen in P2O5. I multiply that by the fact that 16 AMUs per 1 atom of oxygen. The molar mass, or not the molar mass, the formula mass of P2O5 is 141.94. Did we lose anybody there? I'm just adding up the mass of P2O5. It's 141.94. What's the mass of the actual formula? 283.88. If the mass of the empirical formula is 141.94, the mass of the actual formula is 283.88. It was reduced. The empirical formula was reduced by a factor of 2. So if our empirical formula is P2O5 and it was reduced by a factor of 2, I just take 2 times 2, that's 4. 5 times 2, that's 10. The actual molecular formula would be P4O10. So if you know the empirical formula, you add the mass up of the empirical formula. They must tell you the mass of the molecule or the molar mass of the actual molecular formula. You divide the mass of the real one divided by the mass of the empirical. That will give you what it was reduced by. That's all you have to do. We have some practice problems to work on. I think it's 6D what? Is it 6D16? We cut the assignment in half from what it normally is. That assignment's usually 4 pages. We just cut it down to 2 to give you a chance to practice this today and to not bog you down with excessive amounts of homework, as today ends the 3rd quarter. So if you're trying to catch up in any of your classes and your teachers are allowing you to turn in late work through Sunday or whatever the day might be, make sure you're catching up. If you are missing assignments from this class, when were they due? When? Missing work for this class was due yesterday. Yesterday's assignment and today's assignment can be turned in through Sunday. Actually, Wednesday, Thursday, Friday's assignment can be turned in through Sunday. What if you've had extenuating circumstances in your life that I might be unaware of? Could you email me and explain that you've had, and some of you might be like, I email you every time I have something late and I'm always asking for an extension. Well, keep asking. You never know. I may say yes. I may say no. I may say I need more information because this is becoming a habit. I don't know. But if you have assignments that are missing, you can always ask for an extension. Good luck with the homework. The answer key is posted so you can check as you go to see how you're doing. Every number needs a what? Label. Make sure you're doing that.